Hi everyone, welcome to my LeetCode for Beginner video series. So if you're a newer programmer or you're a self-taught programmer who don't have a lot of experience with LeetCode, this is a series for you. LeetCode is a platform where you solve different programming related questions. However, to get a submission in, you'll need to write fast and efficient code. Each week we'll be solving a new LeetCode problem that covers a different algorithm topic or data structure, and we'll discuss how we can optimize the code and different technique you can use to write efficient code. Though this is aimed toward beginners, I do expect most people to have basic programming knowledge and know how to write programs. So I won't be covering, for example, how to do a for loop or so on. So since it's the first episode, I think it's appropriate we start with the number one question on LeetCode, and to me, one of the best question in programming, and that is the two-sum problem. So what exactly is the two-sum problem? Well, it's quite straightforward actually. You're given an array of numbers and you're given a target. You need to return two indexes whose elements sum up to the target. So in the first example, we have an array of 2, 7, 11, and 15, and we have a target 9. We'll need to return 0 and 1 because the element at index 0, 2, and the element at index 1, 7, sum up to 9. If we are given an array 3, 2, and 4, and we are given a target 6, we'll return 1 and 2 because 2 and 4 sum up to 6. It's important to note that the array is not sorted. We'll have exactly one solution, and we may not use the same element twice. So if you know programming, it's actually quite straightforward. You can just loop through the array and then do another loop to find the second element that adds up to target. So in Java, we'll be using Java as the programming language. It will be a loop over the numbers and a second loop starting at the next element after the first loop. So because we can't use the same element twice, there's no point comparing an element with itself. So we'll just compare it with the next element, j++. And if those two numbers add up to the target, we simply return the two indexes. And since we'll always have a solution, theoretically we can't reach this line. However, to compile the code, we'll still need to do something here. In my case, I'll just return an array of -1, -1. Cool. So this looks good, looks correct. And if we run against the test case, we get the expected results. And if we submit it, we actually get a submission true. However, this isn't an efficient code. It's not the optimal solution. And fortunately, Java is actually quite a fast language, so we actually get 0 milliseconds, and it's faster than all of the submission because you can't go any lower. But if we switch a language to something that is not as fast, for example, Python, so this is the exact same code in Python, and if we actually submit this, we will see that it actually took 32 milliseconds. And there is actually a solution that we can get that makes it 0 millisecond even for Python.
Alright, let's take a look at the two-sum problem in detail. So this is our array, and this is our target value. What are all the comparisons we have made? So in our loop, I starts at 2, j starts at the element after that, which is 7, and we'll start comparing from here. Well, luckily in this case, the first comparison we made, we get our solution. So 2 and 7 sum up to 9, so we can just return that. However, as you can imagine, we are not always this lucky. So if our array was something like 11, 15, 2, 7 instead, and we have the same target value 9, well, we'll be comparing 11 with 15, 11 with 2, 11 with 7, 15 with 2, 15 with 7, and finally 2 with 7, and we'll return that. This isn't a problem here because the array is relatively small. However, as you can imagine, if the array has 1,000 elements, we'll be doing a lot of comparison. We could actually capture this with something called the big O notation. This states how big does the algorithm grow relative to the problem size. So our solution is actually what's known as a ordered n squared solution. N here is the size of the problem. In our case, it's the size of the array. And this says that for an array of size n, we'll be doing n by n comparison. So for example, if we have an array of size 2, we'll be doing 2 by 2, which is 4 comparison. Not exactly, because we are starting from one element less, but approximately n by n comparison. If we have an array of size 3, it will be 9. An array of size 4, it will be 16. An array of size 100, it will be 10,000. As you can see, the problem grows significantly as our array grows. So is there a way we could lower the number of comparison? Well, let's think about it. If we have a target value of 9 and we came across the value 11, what do we need to add on to 11 to get 9? Well, if you know basic algebra, that's basically 9 minus 11, and that's actually minus 2. So if we can quickly or efficiently look up whether we have a minus 2 in our array, then we could quickly find a solution. So how will we do that? Well, this is the first data structure I'll be introducing in this series, and that is arguably the most important data structure in programming, and that is a map, or some call it a hash table. So what is a map? A map has two parts. It has a key and it has a value, and each key maps to a value. Keys are unique, so each key will always map to a value, so you won't have two same key mapping to two different values. And it is this uniqueness that makes map important, because maps has the property of instant lookup. So regardless of the size of a map, you could have a map of 1,000 keys or a map of 2 keys. Looking up whether a key is in a map and what its value is always instant. It takes the same amount of time. So let's take a look at an example of a map. So we could have a map of ID to a name, for instance. Imagine you're in a company and each employee has an ID, and the map could look like the ID 1 points to the name John, the ID 2 points to the name Alan. And you could have 1 million employees in your company. Looking up the name of employee with the ID 1 is always instant. Or you could look up whether a certain ID, for example the ID 123, does it exist in the map. So a map is crucial in a lot of different algorithms, and we'll be looking at how we could utilize map in the two-sum problem. So let's go back to the array. 9. So what is the map we want here? So we want a map from value to index. So remember the indexes of an array, 0, 1, 2, and 3 in this case. We want to map 11 to its index 0, 15 to its index 1, 7 to 2, and 2 to 3. So if we define a map which starts off at empty, we could actually find a solution just by doing one loop. So remember the algebra concept I introduced earlier. If we came across the value 11, we know we want the value 9. So what do we need? We need minus 2. 9 minus 11 is minus 2. We look in the map and we don't have a minus 2 in the map, so we don't have a solution. And after that, we put 11 into the map, pointing to its index of 0. And then we move on to the next element, which is 15. So to get 15, we will need minus 6 in the array. So because x in this case is minus 6, we look into the map, we don't have a key with the value minus 6, so we don't have a solution. And similarly, we put 15 into the array, pointing to its index 1. We move on to the next element. We need to add 2 onto 7 to get 9. So, and looking into the map, we don't have the element 2 because remember we are here and we haven't reached the element 2 yet, so we don't have a solution. And we add 7 into the array, pointing to its index 2. And finally, we reach the element 2. We need the value 7 in the array. And if we look into the map, we have a key with the value 7, and that points to its index, which is 2. And because we are in a loop, we know that we are currently on the index 3, and putting that together, we have the indexes which are 2 and 3, and that is our solution. It may seem similar to what we have done previously using the to for loop, but because of the instant lookup we get using a map, we are essentially only doing the loop once because we compare. It's not in the map, we move on. If it's in the map, we return. So that's how a map could make our algorithm a lot faster. Finally, let's take a look at the time complexity of the mapped solution. So remember previously with our double for loop, we have a complexity of order n squared. So what is the complexity here? Well, remember, looking at our map is instant, and in big O notation, instant is written as order 1 because it's always take one element of time regardless of what that time element is. And how many times are we looking into the map? Well, for each element, we are looking into it once because if it's there, we return. If it's not there, we move on. So it's for order n times, we are doing an order 1 operation. So and that basically equates to an order n solution. So if we have 10 elements in the array, we are doing 10 comparison. If we have 100 elements in the array, we are doing 100 comparison. If we have 1,000, we are doing 1,000. Remember in our previous solution, the order n squared solution, if we have 10 elements in the array, we are doing 100 comparison. If we have 100, we are doing 10,000. So as you can see, we dramatically reduced the comparison we are making in our solution.
Alright, let's try to code out our optimal solution. So we need to define a map, and in Java, a map, we could use the collection framework which has a lot of different data structure, and one of them is a map. So to define it, you define it using generics. If you are not familiar with Java, that basically means defining a map from type integer to type integer. So the key is an integer and the value is an integer. And we'll be using a hash map. There are different types of map, but for most cases, a hash map is the one you want. We'll be covering different maps later on in this series, but hash map is the map that gives us the instant performance. So we have our map and we just need to look through the array. And to find the complement, we subtract the target with the current value we are looking at, which is the element at I. And to look up in the map in Java, we could use the keyword. The method contains key to check if an element is in the map. So this returns a boolean, and if comp is in the map, then it returns true, otherwise it returns false. So if comp is in the map, then we have our solution. We just return an array of the indexes, so index I, which is the one we are currently looking at, and the element that's pointed to by the complement. So map.getComp will get the value that's pointed by the key comp, which in this case is the indexes of our second element. If comp is not in the map, then we will continue on with the loop, and before we do that, we will need to put the current element into the map. So map.put puts elements into the map, and what we want is we want to put the current element nums I, and we want that to point to the index I. So let's try and run the code and submit it. Yep, we got a successful summation through. The two-sum problem is a simple problem, but it shows many important concepts such as how using extra memory, in this case a map, could improve the runtime of our algorithm. However, because of this simplicity, I can't quite demonstrate how it improves in terms of speed, but in the future we'll be looking at more complex problem where a different approach significantly reduces runtime. That's all for this video. Hopefully this will be a recurring series on this channel, and we'll be solving more complex problems in the future. Until then, happy coding.